Today is we're going to look at measuring the magnetic field strength of a magnet using F equals Bill. So what I've got here is I've got a balance and I've got a magnet on top of the balance, and you'll notice that the magnetic field is going from north to south. And so if I put the compass on here, you can see it's going from north to south. So that's north, that's south. So putting the magnetic field on like that, we can see the magnetic field goes that way. Now, what we want to do is we want to create a force on this wire, and we're going to measure that force. And so we need to put a current through the wire. Now, I want the current to produce a force actually that goes up, because I've clamped this wire. So this wire is going to experience a force upwards due to the current in the magnetic field. But because that wire is clamped, what will happen is Newton's third law says that objects experience an equal but opposite force. So if this magnetic field forces the wire up, then the wire will force the magnetic field and the magnets down. And because the wire can't move, the magnets will be pushed down with identical force, and the balance will read that increase in force. So what we want to do is to make sure the force is up. So using your left hand, the first finger is field, the thumb is force or motion, which is pointing up, which leaves the current pointing to the right. Newton's third law says if this wire experiences force up and this wire can't move, that wire will push the magnet, and so that will push the magnet down, and that will increase the force. So what we're going to do is we're going to change the current down, and we're going to measure the mass, increased mass, times it by gravity, and that will give us the force down. And by plotting a graph of force against current, we can see the relationship, but also work out the magnetic field strength of the magnet. So what we're going to do is I'm going to go up in 1 amp at a time, and if you watch carefully and record down the mass as we do it. So the current at 0, and I'm going to tear the balance. So adjusting the current to 1 amp gives us 0.2 grams. Increasing the current to 2 amps gives us 0.4 grams. Increasing the current to 3 amps gives us 0.6 grams. 4 amps gives us 0.7 grams. 5 amps, 0.9 grams. Increasing the current to 6 amps gives us 1.0 amps. Increasing to 7 amps gives us 1.2 grams. And finally, increasing to 8 amps gives us 1.3 grams. Now, if I just remove all of these, and we'll just measure the length of wire in the magnetic field. Remember, it won't be exactly accurate because the magnetic field does actually come round here and here, so you've got a bit there and there. But if we just do it for the wire that's actually in this part of the magnetic field, I make that 6 centimeters. Because the balance only measures to 1 decimal place, our points are slightly scattered, and therefore drawing a best fit line has the same number of points one side as the other. You can clearly see that force is directly proportional to current, but I want to look at the graph in a bit more detail, which may be what you'll get at the highest level questions. So we've got a change in mass which is equal to 1.38 grams. Now this needs to be converted into kilograms, so we're going to divide by 1,000, which is 0.00138 kilograms. Now we plotted the mass increase of the balance, which is proportional to force, but I want to work out the force. And remember, force is mass times gravity. So we're going to times that mass by 10, which will give us 0.0138 newtons. So if we were to plot a graph of force against current, we would have got a straight line going through the origin, show they're directly proportional, and on the y-axis, would have got the value of at 8 to be 0.138 newtons. Now force is equal to BIL, magnetic field strength, times current, times length. So if we plot it as y equals mx plus c, we plotted F on our y-axis, we plotted on our x-axis current I, so our gradient is B, the magnetic field strength, times by L. So BL is the gradient, which is equal to F divided by I, and our force was 0.138 newtons. Our current was 8 amps, which gives us a value of 0.00173. So to find the magnetic field strength B, we're going to divide through by the length of the magnetic field, which was 6 centimetres, which is 0.06 metres. And that gives us a value of the magnetic field strength as 0.029 Teslas, which is given the symbol T. So that shows how you can use the graph of force against current to work out the magnetic field strength of the magnets, knowing the length of the wire in that magnetic field.